Okay, so let's think about prime numbers. Obviously, our first question is, what is a prime number? Well, the rules are, or the definition is, a prime number is a number that's only divisible by 1 and itself. So if we imagine taking a particular number, let's take the number 7 for example, I've now got to see if I can divide this by any other numbers other than 1 itself. So I've got to do the test. So obviously we don't do 1 because that's every number is divisible by 1. We obviously don't do it by itself because every number divided by itself is 1 anyway. So we're going to have to do the test. We're going to have to do 7 divided by 2, 7 divided by 3, all the way up to 7 divided by 6. So let's just have a quick think about those. 7 over 2, 7 over 3, 7 over 4, 7 over 5, and 7 over 6. Let's think about what they equal. Now, I'm not actually bothered about the answer. I just want to know, are they divisible? Now, obviously here we mean whole number division, because every number is divisible by something. It's giving me a fractional answer. I'm not interested in that. I want to know, is it a whole number division? And obviously the way that we can test if it's a whole number division, does it go in a whole number of times, is to look at the remainder. And we're fortunate that in Python we have the modulus function, the modulus mathematical operator, that tells me what the remainder is. So if I do 7 mod 2, it obviously gives me a remainder of 1, because it goes in 3 times remainder 1. If I do 7 mod 3, this goes in twice and leaves me a remainder 1. If I do 7 mod 4, 4 goes in once and leaves me a remainder 3. 7 mod 5 goes in once and leaves me a remainder 2. 7 mod 6 goes in once and leaves remainder 1. So because all of these were non-zero, I can see that as I try to divide 7 by 2, 3, 4, 5 and 6, i.e. all the numbers except 1 and 7, none of them went in, because it all gave me a remainder. So what can I conclude from that? 7 is a prime number. Okay, just to chuck another one at us, just so we make sure we understand it. If I now was to do the same again, but think about the number 8, what would I do? I would do the same. I would start at the value 2. I would go all the way up to the value 7 this time, and I would do the divisions again. I would say 8 divided by 2, 8 divided by 3, and so on. Remember, in Python it's a modulus function, so 8 mod 3 and so on. So 8 divided by 2, or modulus 2, that goes in 4 times, and the remainder is 0. So because we've got a 0, we can say that 8 is divisible by 2. Therefore, we know 8 is not a prime. Okay, so on the basis of that, we need to think about what our construction will look like now, and how would we think about writing code to do this. What would our flow be, and really try and think about the computational processing that goes into doing this calculation. And by having played with it beforehand, we should now have a pretty good idea about how we're going to approach this. Because given a particular number, in this case 7, I need to start at 2 and go all the way up to 1 less than the number, and basically do the modulus. Here I started with the number 8. I want to test the number 8, so I started with 2 and went all the way up to number 7 and test the modulus. If at any point I discover that the number mod, whatever my loop value is, because obviously this is going around a loop, is 0, at that point I can go, right, it's definitely not a prime number. So thinking about it, I'm essentially starting with the premise that it's a prime number. I'm doing these tests, and at any point when I do this arithmetic, if I find that the modulus is 0, that's it, it's not a prime number and I can exit. In fact, I don't even need to continue doing the rest of these, because 8 was divisible by 2 with no remainder, therefore it wasn't a prime and I can exit my loop. Think about that. So in terms of our general construction, you can see it's going to be some form of loop construct to do this. So obviously something is going to go on inside our loop here. We're going to be going around our loop. We're going to be coming in initially with some particular number that I want to test. I'm going to go around my loop with a loop value, a loop variable. I'm just going to call it n here. And that's going to go from 2, 3, all the way up to num minus 1, because obviously I don't check the number itself. And within my loop, what am I going to do? I'm going to be testing to see if the number I'm checking, the variable num, mod my loop counter 2, 3, 4, 5, 6, and so on. So that's my loop counter n is equal to 0. I'm going to be doing a test on that. And if the answer to this is true, i.e. it is 0, I know that num is not a prime. And as I said at the start, I'm going to make the assumption to start with that num, I'm going to make an assumption that num is a prime. So I start assuming num is prime. I go around this loop here, checking these variables all the time. If at any point I get a 0 modulus, it's obviously divided into the number. I can assume it's not a prime. And if possible, I don't actually need to continue around the loop. I can at that point, if it's possible in code, exit. When I come out the bottom here, I can see what this num is prime is. Because clearly as it's been round here, if we never get this 0 division, we know it's we're never going to do this statement here saying it's not a prime, so it will still be a prime. So that's kind of our computational thinking idea. What bits do we need to think about how to turn this into code? Well, obviously here we've got some form of loop. It's going to probably be a for next loop, because it's going to go around these in sequence for this number next, going up one at a time to 1 minus there. This here is going to be our test of equality, so it's going to be a double equal sign in our code. Just thinking about our is prime and is not a prime here. Really what we're saying is we want to start with the assumption that num is a prime. So we can kind of think of it being a prime being true. So we're going to think num is prime being true to start with. And as it goes around this loop, if we discover that the mod gives me a 0 answer, then we know at that point it's failed, it's no longer prime. So when I say num is not prime here, really what I want to say is it's not num is not prime. I've got this concept here, num is prime. So really what I want to say, num is prime is false. And straight away now you should hopefully see that we're lending this to the idea of it being a Boolean variable. So there's our basic concept. And at the end of this loop, it's gone around here, it's not found any modulus 0 answers. We won't have set num is prime to false. It's still set to true, so it will fall out the bottom here being true, and that will end our code. If at any point it did give me a 0 division, we would have set num is prime as false, and we would have exited our loop and come down to the end here and exited. Okay, so what we need to do now is look at how we can turn that into code. Okay, so let's have a think about how we're going to code that now. We understand our is prime function. So we started with the premise that our prime number was true, so we probably need a variable called is prime. Now actually we can't use is prime as a variable name, we've already got it as a function name. So let's just have prime. We're going to set it to the fact that initially it's true, so we started with the premise that it is true. Then we need to go straight into our loop for n in range. We said we're going to start with 2 because we know it's divisible by 1, and we said we wanted to go up to num minus 1. So we actually know that if we put in the variable the value num here, our loop won't actually go all the way to num, it will go up to 1 less. So actually that satisfies our case straight away. And We want to do the test to see if the number we're testing, mod, so remember this is our remainder, so mod, our loop variable, which is n, is equal to 0. So if this test here gives me a 0, I know that it's not a prime number. So I could assign this expression now to a Boolean variable, but I could just use it straight in a loop. So I'm doing my test if num%n is equal to 0. Again, you don't need to do this, but for me sometimes it makes it a bit clearer so we know what's going on. I'll put that in parentheses. So if that is true, what do I need to do? Well, the variable prime now I can set to a false value. I know that that's the case. It's clearly going to go round the loop. We're not going to exit at this stage. We'll come back to that in a moment. It's going to go round the loop. Now if it goes round again and finds the next one doesn't fail, and the next one doesn't fail, it doesn't matter because we've already set prime to false. No way in here can we set prime back to true. We only set it at the top. And then obviously at the end of here, we want to return the fact that it's, sorry, not false. We want to return prime, which is our Boolean variable. So let's see if that works now. Let's run our module. Okay, so our next value to check, we'll go for 10 again and see what happens. So it's telling me 2 is a prime, 3 is a prime, 4 is false, 5 is a prime, 6 is false, 7 is a prime, 8 and 9 are not primes, and 10 is not a prime. So that looks pretty good. Let me just run it again. I'm not familiar with my primes. I do know that 17 and 19 are prime, so I'm just going to run my module and put 20 in there and see what happens. So here's 17 true. Oh yeah, it's a prime. 19 is a prime. That looks pretty good to me. 13 is a prime. 11 is a prime. So that looks like it's giving me the right kind of answer. So just going quickly back to our code here, from an efficiency point of view, and you don't do this, it's not kind of a massive problem really. Clearly, once we've discovered that it's not a prime number and we've set prime to false, we don't really need to continue going around this loop, but the loop will continue all the way up to the value num-1. Well, there is a way to get out of loops when we've had enough, and we can actually break out of a loop. So you can break out of a for loop at any point by using the break command. This obviously only happens if we've discovered that it's no longer a prime number because there's a modulus value of 0. So we set prime to false and then we break out of our loop. So it's just a marginal improvement on the code there. Let's just check that still works and we've not made it do anything silly. So I'm going to put a value in there. And let's just check 7 is still a prime, 11 is a prime, 13 is a prime, 17 is a prime, 19 is a prime. Great. So you obviously don't see any difference there because it's quite marginal. But if we were putting particularly large numbers in here, you'd see that actually speeded things up considerably when we came to calculate those answers. In fact, just out of interest, we'll just do that now. I'm just going to comment out the line. So we're going to ignore that break. See if we can actually see the difference here. I'm going to run it here and I'm going to put in 100 as my value to check. Wow, that was just too quick anyway. Obviously I'm going to have to put in huge values here I think to see the difference. Obviously our numbers here for the factorials are going to get huge. So just as a test at the moment, I'm not going to do the factorial. I'm just going to make that return 0 every time within our code here. I'm just going to rerun the program and I'm going to put in 10,000. In fact that's 100,000 and see what happens. Okay, so it's still so quick we really can't see any difference yet. That's pretty impressive when you think here we are getting up to values like 2000 and clearly it's doing all those divisions at a kind of lightning speed really. we're not able to see the difference there. So if we're using this as a test, it's now quite difficult really. It's not conclusive. What we'd probably have to do is time it. We'd have to time it maybe up to 10,000. We'd have to time it then with and without that loop. So there you go. It's, you know, I've been talking for a little while. It's just got to 5,000. I'm going to execute that code. I'm going to put in this break back in now, which should speed things up considerably. I don't know if we're going to see the difference. It's going to be quite difficult. So I'm going to put in that 100,000 again. Obviously I didn't let it get there. So remember, I got up to 5,000 quite quickly. So here we're running. Yeah, I don't feel this is particularly conclusive. I think really to prove this, I'd have to put in some really big numbers and measure the difference. Okay, well, that was worth a little go, but I don't think that was particularly conclusive. We'd have to find and really prove that that was making a difference. Okay, so that's our basic program. Can we make any improvements on that? Well, let's just have a quick think about that.